Okay, great. So good morning, everyone, for our distinguished webinar series in AI and cybersecurity. Today's speaker is Dr. Kirill Morozov, Associate Professor, Department of Computer Science and Engineering, University of North Texas. The title for today's talk is Using Untrusted and Unreliable Cloud Providers to Obtain Private Email. Dr. Kirill received his MSc in Telecommunications Engineering from St. Petersburg State University of Telecommunications, Russia, and PhD in Computer Science from University of Aarhus, Denmark. After working in various research and academic institutions in Japan, he joined the University of North Texas as Associate Professor in November 2017. His research is focused on cryptography and cybersecurity. Dr. Morozov's research and academic activities are funded by NSA. Dr. Morozov's area of expertise is cryptography based on coding and correlated randomness, including code-based post-quantum cryptography, secret sharing schemes, and information-theoretic primitives based on noisy channels. He is known in particular for constructions of oblivious transfer, an important building block for secure computation based on any discrete memoryless channel. His other contribution is the semantically secure variant of McEliece public key encryption in the standard model, which served as a departure point for various code-based cryptographic protocols. Dr. Morozov's current research interests include blockchain, automotive security, and security in additive manufacturing. Dr. Morozov, thank you so much for taking our request or invitation and presenting for this webinar. I am so honored to have you as part of the UND's webinar series. And the floor is yours. And we have about 45 minutes or 50 minutes, depending on how long you want to have your slides, and then maybe 10 minutes for Q&A.
Okay, thank you. So thank you for your introduction, Dr. Ranganathan. It's both privilege and a pleasure to present at this seminar series. It's the first time for me. Unfortunately, I've never been to Dakotas, but I hope that one day I will visit. I believe in summer, it should be.
You should, yeah.
Much more cool than in Texas. So let me share my screen now. Do you see my screen or not? You still see the...
I can, but it's not in full screen.
Right, it's not a full screen. Just a moment. I believe. Okay, so I think. Just a moment. My apologies. Yes. So how about now? It's still not the full screen. Yes, I can figure. Okay. I need to...
You just have to go to display settings.
Yes.
And on the top.
Correct.
And you're fine. I think how is it?
I need to ask to... Just a moment.
I think from the Zoom page, if you go to the top display settings, you can swap the monitor.
Oh, okay. Yes. In Zoom, I need to go to
like present.
Jameson, do you think you can request remote control and find out?
Just a moment.
Are you allowed to do that with Zoom?
Okay, I can do that. Let me see if I try.
Their display settings.
Oh, okay, right. Thank you. My apologies. Okay, yes. So I need to do duplicate, right? Okay.
Is that the...
I think swap presenter and...
Yeah.
Which one? I'm just clicking on it. It's not...
He's also clicking. So.
Can you try Dr. Kirill?
Oh, okay, yes. Swap presenter view and slide view. There we go. Yeah.
Oh, there you go.
Okay. My apologies. Technologies. I'm growing old, so I do not catch up very well. So good morning, everyone. So I'm I'm Kirill Morozov from the University of North Texas, and today I would like to present our recent work published at SECREPT 2023, using untrusted and unreliable cloud providers to obtain private email. This is a joint work with Nicolas Chiapputo, for whom it was basically the senior thesis, and Dr. Ivo Desmet from the University of Texas at Dallas. I was planning to do a self-introduction, but actually Dr. Ranganathan already presented my brief bio, so I will just quickly skip through that. I'll go to research talk about 35 minutes and then Q&A as long as it will take. So this is my bio, basically presented before. So yes, I joined Department of Computer Science and Engineering at the University of North Texas in November 2017. Before that, I worked for about 12 years in Japan. For my research, I can the colors on the slide basically show my level of confidence if you ask me to present those topics. So for my PhD studies, I worked on cryptographic protocols based on coding and correlated randomness, basically cryptographic use of noisy channels. So if we have a noise in the channel connecting the parties, we could use it for security applications. Later, I switched to working on cryptography based on coding, such as security of McEliece encryption scheme and also secret sharing schemes. So today I will present applications of secret sharing scheme to secure distributed storage. The idea in general is not very novel. It has been suggested before, but in this particular scenario for secure email, it is not commonly used, but I believe that this idea has a lot of potential, and therefore I would like to share it with you. Also, I worked on privacy preserving computation. This is if you would like to have your information in cloud but encrypted, you could still do the computation on it. For example, run network analysis algorithms on encrypted graphs and so on. I also worked on blockchains and reputation-based consensus. The idea there was, what if we would like to make participation in blockchain is a little bit more democratic, in the sense that anybody could join as long as they're doing good behavior, rather than possess a lot of stake, like proof of stake, or a lot of hash power, like in Bitcoin, and hence the work on reputation-based consensus. Recently, I started to work on the topics like automotive security, knowing that communication inside our vehicles and drones is completely unprotected. Then the idea is to just basically map internet security that we already very well know for computer networks for this embedded scenario. But yes, this is my research overview. I'll go to the topic of applications of secret sharing for secure communication. So the basic punchline that I'm going to deliver as a motivation for my talk would be concerns, kind of some standard concerns. What if email provider reads your emails? So of course they can do, because they can do it. They have access to your information. Even if you trust your provider can be hacked, unfortunately, and that happens relatively often. And also what can happen at the same time, luckily, yeah, it doesn't happen too often, but if the data provider loses data due to a natural disaster or again some hacking attack, then, you know, like, again, my data would be lost unless they are backed up. So I would like to offer some solution for that in a minute. Before that, I would like to just further motivate my presentation by claiming that email security issues is also a major problem, as shown by the recent Verizon report on data breach investigations. So I can, I want to be entirely honest here. I suppose that, so email is going to be an attack vector, as shown in the report from the last year issues. It's contributes to about 30% of attack vectors, and the loss of information is a big issue as well. I would probably claim that it's mainly due to phishing attacks. However, the report shows that email security issues are one of the major issues that we need to take care of. And the loss of information is one of them too. So encryption, yeah, of course, that's the cryptographic mechanism that we use for confidentiality in the internet, but it's only a partial solution because it needs the key, and hence it needs a mechanism to establish the key. We need to run key exchange. There is always the so-called fail opening problem. So if the email server does not support encryption, typically the data will not be encrypted, you know, to prevent denial of service. And also, yeah, the so-called computational security has various technical challenges. What algorithms or what parameters to use, they may change according to the jurisdiction. Different jurisdictions may have different standards. We need always be aware of recent attacks, such as attacks using maybe quantum technologies. So all of this can be avoided if we look at the technology that has been known since 90s, and it is called perfectly secure message transmission. So the idea basically is to get security, like in one line, we get security from path diversity. So suppose that sender and receiver are connected using n disjoint paths. So somehow they are able to communicate over n different channels. And we assume that the adversary physically is only able to control only some of them, but not all of them at the same time. So Dolev, Warts, Naor, and Jung showed in '93 that as long as we have the honest majority of the channels that are not controlled by the attacker, then we can have secure and reliable transmission in this case. So in this presentation, what I will do, I'll just basically map this into the email communication scenario and explain how security can be achieved using the so-called secret sharing technology that I will present in a way. So this picture has a lot of text, but basically what you could see, I'm just mapping the scenario that I have shown you on the previous slide into the email communication between the sender and the receiver. So you could just pretty much ignore the text. What they will do, they will exchange emails over different email providers. So think of 3 email providers: Google, Yahoo, and I don't know, say Baidu, for example, right? To split over different jurisdictions, and they will be just sending the emails, right? So in this case, we have 3 disjoint paths, assuming that the attacker do not control all of them. And so we'll try to provide security for communication between, as a simple example, we could extend it over more providers and higher threshold for the adversary. But now we assume that one of the providers turns rogue or being hacked, and therefore they can leak your data, okay? So then, you know, like if you just copy the information, send exactly the same thing, then you have reliability, but no security, because one provider will be just leaking your data. So how to resolve this problem? Of course, yeah, any protocol for perfectly secure message transmission solves the problem, and there has been a large body of works for different scenario on this topic. I will not be the best person to explain the details, but if you are interested, you could look at the recent thesis by Erotocrito, and he has a very good survey of recent results in this area. In our case, the most basic of the protocol for PSMT was implemented, and it can work in practice, and I'll show you result towards the end of this presentation. So the closest related work of applying PSMT, or more specifically secret sharing, for secure email communication was unpublished work by Oren and Wool. So it's just a report where they use, yes, as I mentioned, secret sharing to protect emails. I'll present secret sharing next, explain you how it works. The disadvantages of their work is that they cover only 2 providers, and they don't have data integrity. So if one of the providers starts sending random stuff, then it will be might be accepted by the parties. A definite advantage of the result is that they use the so-called linguistic encoding. So what it means is that the emails that they are going to be send over different providers, they will be meaningful messages. So if the parties are under surveillance, then they will be able to send the messages that is kind of hidden inside their communication while the messages look innocent. In our case, the pieces that we are going to send over the disjoint paths, they're going to be random. More details about that in a moment. So the technology that I would like to present is a well-known cryptographic protocol that is called secret sharing. It has been presented independently by Blackley and Shamir in 2 different publications in the same year, 79. It's a very old technology. It allows a dealer, that's the original term that we use. Basically, this is the data owner who has some secret data, to split the data into different pieces. So different pieces, which are called the shares of the secret, they could be seen as a kind of pieces of puzzle. You know, so each piece of a puzzle goes to the individual party, except that compared to the physical puzzle, on the physical puzzle, if it comes back to some picture, then you could see a part of the picture from a piece. However, in the digital world, in secret sharing, a piece gives you no information at all until you collect many enough pieces that comprise the so-called access set. So the access set will allow efficient reconstruction, and all the data will be recovered this way. So the algorithm for splitting the secret is called shared generation algorithm. Yes, the pieces go to parties, which in our case will be email providers. So when needed, the parties will be able to run the reconstruction algorithm. So in practice, it could be just the access set of parties that pull their shares together and reconstruct the secret. In our scenario, they will just forward, being the email providers, they will just forward it to the reconstructor, and the reconstructor will be the receiver. So they will run this algorithm and get their secret back. So next question is how to do that. In the digital world, there are many designs, and I will present you the Shamir scheme because it's kind of easiest to understand. It's a classical example. So what we do, we work over the finite field. For simplicity, you could think of just working over integers. P is going to be modulo. So it's just a modular arithmetic computation modulo P. P is going to be some large enough prime number. So we take the polynomial, and in the polynomial, we choose coefficients of the polynomial at random. The degree of the polynomial must be T. That's exactly how many adversarial providers we would like to tolerate. And the secret will be a free coefficient of the polynomial. So we'll be doing the basically computations over the integers. And now every share of the secret is going to be just a point on the polynomial. So point at 0 will be the original secret, and the point at 1, for example, evaluation of the polynomial at 1 will go to the party 1, evaluation of the polynomial of 2 will go to the party 2, so S1 is here, S2 is here, and so on. So reconstruction is just Lagrange interpolation. So we know that if the polynomial has degree t, then any t plus 1 point will give us back the polynomial itself, and therefore we'll get the free coefficient and get our secret back. For privacy, I'm not going to go into details, but it's possible to show that any subset of t parties has no information about secret. So let me give you a simple example. Think of a line, you know, like representation on the two-dimensional space is not working because we do the modular arithmetic, but yeah, think about the line. Then any 2 points on the line allow you to reconstruct the line, and therefore you get the free coefficient back, right? So reconstruction works. For privacy, if I give you 1 point on the line, then without any extra information, you would have any slope that is possible, right? So basically, if you don't know any other point, then the secret could be any value. So literally, the scheme is going to be secure in the information-theoretic sense. There is no way to break the scheme. There is no way to do the brute force attack as compared to the regular cryptographic constructions. Without getting another piece, you have no information about what the secret is. That's the advantage of those types of schemes. Back to the scenario, right? So that's what we are going to do. Now, at least some of the text here makes sense because inside the email client, we will have a program that runs the secret share generation algorithm that I just presented. You could do Shamir, for example. We'll do something a little bit more advanced. Sorry. And then basically the email client will just send not your original messages, but rather pieces of your message in the normal email, right? So every provider will get a piece, and from that piece itself, because every single provider will not be able to reconstruct the secret, then they will not be able to see what your email is. They will forward it to the corresponding account. And now Bob, a legitimate receiver, will get the data back, run the share reconstruction algorithm, and get their email, okay? So security will follow from the fact that less than a threshold of providers, in our case, threshold is 2. So if you get the pieces from any 2 providers, you're good, you can do the reconstruction, and any single provider will have no information about your message, okay? So you could play with it pretty much with any email provider is going to be like technology agnostic in this sense. Right, so note that here there are no pre-shared keys between sender and receiver. We have security in the information theoretic sense. Security depends on the fact that is based on the fact that the providers do not cooperate. You know, if they cooperate together, then they will be able, of course, to reconstruct the secret data. Okay, so we got privacy. That's good. Now, what we would like to have, we would like to have reliability. So we would like to have protection against malicious providers. And what the malicious providers can do, they don't have to send exactly the information that they received. So what they can do, they can basically send a different point, right? So they basically replace your email. Now, at the reconstruction, Lagrange interpolation will give you a different polynomial and therefore a different secret. So we would like to prevent that. Solution is adding the property that is called robustness to the secret sharing scheme, and that's also quite an old idea from '89 by Rabin and Benor. We can show that actually, again, if we have the honest majority, or more specifically, if we have for every one path that is controlled by the adversary, we have two paths which are not controlled by the adversary, then we can actually tolerate T-malicious providers. So idea here is a clever message authentication for each share. And I'm not sure if I have much time to go into details about that. I'll briefly show you how it works, but yeah, not much of proofs or details. Notice, however, that again, there are no pre-shared keys between sender and the receiver. So as long as the adversary does not control many enough paths between the parties, then we will have both security and reliability according to the robust secret sharing scheme. So what we would like to provide? We would like to provide now authentication for our shares. So the sender controls what is going to be sent. So what the sender can do, the sender can add the so-called authentication tag. You could think of it as a cryptographic checksum. Yeah, the receiver would be able to verify it at the receiving end. Everything is fine. Unfortunately, it's not going to hold as long as there is a key pre-shared between the sender and the receiver, right? So that is going to be an issue initially, but yeah, so the adversary who is controlling the channel will not be able to forge a correct authentication tag or cryptographic checksum as long as the key is not known to the adversary. So a great idea by Rabin and Benor would be to say, hey, look, actually, since the sender is going to send all the information, what the sender can do, assuming, say, in the simple three-party case, assuming that only one path will be controlled by the attacker, then what we will do, we will distribute the share itself. So S1, S2, and S3 will be the original shares. And then we will give tags corresponding to two other parties. And then we will also give keys corresponding to two other parties. So basically, if, for example, this provider goes rogue or being hacked, then two keys are going to be leaked. However, there will be always another party who will be able to support the honest person, right? That's the idea. So basically, in the end, we receive the share, verify the tags, and take the result by the majority vote. Since per one dishonest path, there are always two honest paths, then the majority vote is going to work. That's a very high-level idea of how we're going to do it. Universal hash function, yeah, is going to be unconditionally secure again. So no way to break it by the brute force search because everything is in the information-theoretic scenario. We could use universal hash functions or Carter-Wegman message authentication codes. So those original designs were put forward actually in the same year as Shamir secret sharing schemes. Universal hash functions found a lot of applications in computer science, in particular for us cryptographers. They are good message authentication codes. The only problem is that if we look at the original designs that work over integers, they are not really fast. So luckily, in the coming years, there were many fast designs of universal hash functions that are suitable for different architectures like 32-bit architectures or 64-bit architectures. So in our construction, we used the design that is called PolyQ32 by Krovitz and Rogoway. It's convenient because it doesn't require any processing for messages. We just take the message, break it into chunk, and then authenticate it using the cipher. Using the universal hash function construction. And we also can, if we do not mind increasing the size of the authentication tags, we could also kind of control the probability for the attacker to break the scheme. So basically, the more blocks I add, the less chance the attacker has to break the scheme. This is a design here. Yeah, I'm going to skip it, so I will not explain the details much. So what I will do, I will just say that what we implemented an add-on for Mozilla Thunderbird that is now has basically the function of secret sharing the messages. We chose Mozilla Thunderbird because it's an open source cross-platform email client. It's easy to program add-ons in JavaScript, and that's basically what Nicholas did. So the add-on is available in GitHub. You could actually install it, play with it, see how it works in practice. Mozilla has Web Crypto API, so you could generate random numbers and use it readily for your applications. Currently, you could choose the scheme. So in the address book, you could provide the email provider. So basically what you do, you say that if I'm going to send a secret shared email to Professor Ranganathan, I will have to have his name in the contact, and then in the notes, I will provide the email addresses that I will use, where the addresses for which my shares will go. So for Shamir secret sharing, there are only shares. I could choose a 2 out of 2 scheme that is basically splitting the data over 2 providers, or I can choose Rabin and Benor, in which case the tags and keys will be also placed into the attachments. Yes, these are the schemes that we're going to support. There will be 3 emails sent. So at the receiver side, we'll need to figure out the emails that belong to basically, one communication. Then we will have a unique message identifier that is going to be placed into the subject. So every pieces that correspond to the same message will have the same ID. At the receiving side, they will be all collected together, and the information about secret sharing schemes will be used for reconstruction of the secret. So T out of 2 scheme is basically uses 2 disjoint paths, so 2 providers, and protect against one of them being dishonest. In Shamir scheme, we can generalize it. I can have like 10 email providers, and any 7 of them, or any 2 or any 5 can be dishonest. Here we're not protecting in those 2 cases. The providers are assumed to be they could observe our communication, but they cannot change them. If you would like protection against malicious providers, the number of providers need to be strictly less than half of the total number of providers, as I mentioned before. And then you will have to also kind of bear the cost of adding the extra information, such as tags and keys, which is for modern email should not be really a problem. That way you're going to have a reliable transmission. So yeah, we ran simulation results. Yeah, we tried it with the providers. It generally works. And the problem is that what we used kind of some readily available implementation of secret sharing. And we also kind of didn't really optimize our construction. So we took fast universal hash functions, but we didn't do any further optimizations. So basically, additive scheme is going to be just pretty much XORing the messages with a random key, and then sending the masked message and the key over separate providers. So in general, it's pretty fast. So most of the time delay here, you could see sending like 100 bytes is going to take maybe 7 milliseconds, but the percentage of the contribution by the encryption scheme is very, very small. So it's going to happen like really, really fast. And then most of the time that will be the working of the JavaScript, which is not very fast, But as we increase the size of the message. So like if we want to secret share like 500 kilobyte, we'll notice that we are going to have like substantially like much more than a second, like it's going to take several seconds. Especially it will be costly, of course, in case of Shamir and robust secret sharing, and most of the time will be actually the working of the secret sharing scheme. So what it means is that we really need to optimize our implementation if we want to do it for the practical use. But yeah, for the prototype, it's working and you can check it. So limitations. Yes, we are protected. We provide protection against malicious providers, but we do not provide protection from network surveillance. Of course, if we intercept all the communications that are outgoing from the receiver or coming in for the, outgoing for the sender or coming into the receiver, of course, we do not have security because we just intercept many enough shares and get the secret, right? So this protection that we provide will be only against the providers, and otherwise one would have to use standard anonymity techniques or encryption, combine them together with this. Yeah, for example, use steganography or something like that to increase the level of security. Concluding remarks. So the proposed method is an email security mechanism that can be used as an extra line of defense in the defense in-depth architecture. So basically, it can be built in current security email mechanisms and can be used on top of the encryption or overlaying the encryption. You know, that depends on your application choice, but it combines very well. You know, like what we just present is that you will have to use several providers and you will have to allow extra throughputs for your keys and for message tags, but otherwise, you know, like that's the price you're going to pay. Good news, yeah, is that actually any construction from the literature can be applied. And then, yeah, we could try different ones in the proposed architecture and see which one is faster and which one is more efficient. In general, we can tolerate different number of providers. We can trade efficiency for less strict assumptions on the number of providers that will be controlled by the adversary. And yes, as I mentioned, we need optimizations because so far, yeah, our proof of concept implementation is a little bit maybe slow for, I don't know, general public application, but it works. Yeah, so an interesting future work could be actually extending the methodology to social networks because, yeah, if I want to secret share data across platforms, what am I going to gain? I'm going to gain reliability, maybe protection against censorship, because one platform, if I made a publication over 5 platforms and you know, any 2 of them will allow the reconstruction of my data, then I may get anti-censorship protection this way. It's kind of, there are many interesting questions here that comes up with the legal status of publications because our share is actually meaningless. So if I share some random information on 2 platforms and then you can recover it, is it a legal application or does it comply? So what kind of laws it has to comply with and so on. Yeah, that's an interesting question. Kind of circling back to the original Oren Wool's linguistic coding, it actually gives an opportunity for what we can call multi-meaning publications, is that I can publish 2 different texts that will have some innocent meaning, combined together, they will have actually the 3rd meaning, so those who can combine it can get this extra message. Right, so I guess, yeah, anti-censorship application would be one possible application for this methodology. And yeah, so references are here, and thank you for your attention, and I'll take questions now.
Thank you so much, Dr. Kirill, for your presentation. I think it's nice to get some refreshing about Shamir's work and connecting back what you did. So we can take some questions. Maybe I'll start with the, in your 2x2 additive approach, did you talk about, what is the minimum number of shares needed to reconstruct, what the
Very good. So 2 out of 2 scheme, if you think of one-time pad, basically one share becomes the ciphertext and another share becomes the key, and then combining them is just a simple XOR. So 2 out of 2 is just sending information over 2 paths, and then any single share gives you no information at all, but combining them together will give you a reconstruction. It is the fastest because really it's just sharing is an XOR, binary XOR. Reconstruction is the binary XOR, but security is minimal because if you get another one, then you could reconstruct the secret and there is no data integrity.
Scaling this work into social network applications or, in terms of distributing these shares, and are you assuming that there is a secure communication channel? Because there are two points and two perspectives I want to hear from you to see, for where do we storage them? Do we have a secure storage, and how do we ensure the storage of these keys or or not compromise? But two, even if you want to do it in a distributed way, and how do we assess the the communication channel? So I'm assuming you made some assumptions that these are all secure communication channels. I don't know what you think.
Correct. Yes, you're absolutely right. Yes, this is so any network security expert will immediately point out and they will say, look, of course, if I'm under surveillance and then you just basically control all the traffic, then all the outgoing shares will be seen and you will get my secret. That is true, yes. So you're correct that to keep information-theoretic security, we need disjoint channels that are not available to the attacker. Yes, you're right. So in that sense, what I mentioned is that in practice, this security could be used as an extra line of defense. So
what about this conditions of n greater than 2t plus 1? You said for every one adversary, it's assumed that there is at least more than 2.
Yeah.
Thing, the path diversity that you talked about, is that a realistic assumption that still hold in current day and of IoT networks or whatever you talk about,
It's a good question, yes. And again, yeah, this is one of the kind of, it could be seen as one of the main criticism if you start discussing the information theoretic secure schemes, because so yes, how about intercepting communication or hacking into different storage systems that I have? If I have 2 storage systems, even though I shared my data, of course, the hacker could penetrate maybe 2 of the data centers and then get the data. That's a very good point. It's a valid criticism. However, what we are talking about distributing trust and adding security on top that we have now. So at this moment, if you just place your data for reliability in 2 data centers, then the attacker can penetrate either of them and get the data. If you use secret sharing, then you could distribute the trust and maybe, for example, use 3 data centers. You could reconstruct from any 2 data centers. However, the attacker breaking into only one of them will not get your data. So this is kind of an argument that I'm going to use. So I agree, yes, indeed, that how realistic the assumption is will depend on the, say, network security measures. But the technology that I'm talking about will allow us to distribute the trust. That's the point.
Thank you. I think we have a question coming from
Yes.
Dr. Utku. Is asking, I would like to ask, what do you think about applying some behavioral AI-based analysis for inside attackers? Is it possible to derive some predictive outcomes, but about if the inside user tends to use malicious providers or some other mails within email communication?
Okay. Okay, it's an interesting question. I didn't think about it, but it's yes, I think it is possible. I think it is possible in principle, but I believe it would be a really good next step for this research when we will have enough data on the use of such systems. So interestingly, the technology that the technologies that I presented, they're like 40 to 30 years old, and they are not commonly used for current network security applications. So although I know that some of the companies actually introduce them at different points, I know some.
Is it because computational overhead, or is it because of something else,
It is a really good question. I don't know. So it could be because of kind of, one of the reasons could be low awareness of this technology, and another reason could be that one might not see basically how effective the measures would be for the price. However, data storage is not expensive, and we have a lot of data centers, right? So what happened is that what I imagine is that the technology was kind of a little bit the overhead was considered a little bit unreasonable decades ago when the technology was introduced, and now we don't have an issue with storage space, with the number of disjoint paths that we could provide because our networks are very developed. We have a lot of data centers, and so it's not really a problem, except that just like the technology went forward, and one just is not aware about this option. However, yeah, I know that, for example, IBM was offering secret sharing functionality as a part of their cloud service storage. I think they were called secure slice. Yeah, so it was there, and I saw that in their white paper, but I haven't heard of it being used in practice, and not very commonly in other technologies. But I think the idea of distributing trust is the most basic that we can have, and I think it can have good applications for computer security.
Thank you. What is your perspective of quantum, getting over crypto?
Right. So it's a very good point. First of all, the technologies that I am talking about, they are information theoretically secure, which means that, and on the positive side, they're kind of inherently post-quantum. It means that we shouldn't care, like if you use this technology, and if you only look at this particular technology, then they will be protected against advances in classical or quantum computations in the future. So if you don't get another share, you have no way to recover it, no matter how powerful computer you have. So this is an advantage of this technology. And disadvantage is, yes, the absence of keys and basically reliance on physical assumptions about how far the adversary can reach trying to get the shares. But yes, post-quantum nature is important, as long as, so now there is a big caveat, it's very important generation of clean and independent randomness. As you probably know, it is important that the randomness that you are using needs to be kind of not entangled with anything else, so the attacker should not be able to get any side information, because the randomness that I use for share generation, security depends on it in a crucial manner. But currently we have technologies that allow us to generate this clean randomness, or cryptographically good randomness in a quantum safe sense. So in that sense, we have technologies for that. If that will be a concern, we'll be able to overcome this change.
Great. I don't see any other questions coming in. But Dr. Kirill, thank you so much for your time. But before you go, I want just to briefly show you something that I want to help in. Do you see the screen for the IEEE symposium?
I see, no, I see the background.
Okay, let me see. How do I change this thing?
You have to just pull it here.
This one?
Just pull this one here.
Okay. Do you see that?
Yes, now I see it.
We are doing an IEEE cybersecurity symposium in October. I need you to help me review and also help me, submission some papers if you have any, with your students or something, you can able to help in promoting this event, and
Sure.
this is the fourth time we're doing, but I think it's the first time we're doing with IEEE, so any help and appreciation of your support is much appreciated.
Yeah, of course. Please let me know. Yeah, we can talk. Yeah,
we have posters and everything. But for this webinar contribution, you will receive a nice plaque from UND and a nice certificate from our dean.
Thank you.
Thanking your time. But I think it's very interesting that how you are connecting Shamir's work and proceeding in scaling to social network. It'll be interesting to see how the use case for social networks work.
Right.
But thank you so much for your time today, and we'll be in touch.
Yes, thank you for your kind invitation. Yes, and yeah, let's keep in touch.
And you should visit North Dakota. I think make use of this opportunity.
Right. So this symposium could be a good opportunity.
Yeah, I mean, we have a lot of posters, sessions opened, and I'm also trying to reach NSF to see if they give some funding for students so that they can able to get some accommodations. So
very well.
Good.
You have a very nice building there. So yeah, now I really want to visit.
Yeah. Yes, yeah, it's another large campus in the state. It's great. Thank you.
Very well. Yeah, have a nice day and thanks again.
Take care.
Bye for now.